Hello everyone and welcome back to yet another video from my channel Interactive Education. And today we're going to start the next chapter in Mathematics Class 10th SA2 portion, and that is surface areas and volumes. Now this chapter is a very important chapter in mathematics in your Class 10th portion because it has the highest weightage in your SA2 examination. And the best part of this chapter is that it is a completely everyday life based chapter, because it is something which you see everywhere. Your objects, everything is a shape, and calculation of its area, its volume is something you do regularly, right? Now we all know what is surface area, right, from our earlier classes. Surface area is basically the area of the surface of a solid, of the outer surface of a solid. So the area of a surface, or the part of the solid which can be touched, that area, or that can be covered with something, that area is called the surface area of the solid. And volume is a three-dimensional measure which measures the capacity of an object, of a solid, or the space occupied by a solid. So that is called its volume. Now, from your earlier classes in class 8th and 9th, you've learnt about solids, and you've learnt about some basic solids: cube, cuboid, cylinder, cone, sphere, and hemisphere. Let us now look over the formulas of these, and let's just revise them once. So you know that there are two kinds of surface areas. There is the curved surface area, CSA, which is also called the lateral surface area, LSA, right? In case of straight and rectilinear solids, it's called LSA. And in case of curved solids, it is called CSA. And there is also the total surface area, which is the total surface area, including the base also. The volume is pretty much the volume. So I have listed down the formulas of each solid in a proper manner with all the in a tabular form. You can do the same by keeping a table and then putting it down like this, and then sticking it on your study room's wall, or on your cupboard, or even in your washroom, or in front of your bed. So in this way you can see the formula every day. If you are bad at remembering formulas, if you're weak at remembering formulas, this is a very good way. You can write it on a piece of paper in a table form and then stick it on one of your walls, and then if you have a glance at it every day, it'll just come in your mind. That's one way to remember the formulas. The second way to remember the formula is to apply the formula. Now, when you apply the formula many times, that is by solving many questions, when you keep solving and applying that same formula, it just comes in your brain. And that's how I remember it. I keep solving questions, especially when I am in 10th standard myself. I can very well relate to this, that I solve the question of that particular formula or concept several times, many such questions, and then it automatically comes in my brain. Right? So that's a very effective way in which you can remember the formula for any chapter, for that matter. Not only for this, we have some formulas in AP, we have some formulas in quadratic equations are just two, we have some in areas related to circles. So in this way you can either remember the logic, which is pretty complex for some people, or you can just apply it many times, so it just comes in your brain, right? So that's two ways I've told you to remember the formula if you are struggling with that. So let's, without further ado, move to this analysis of this table. So first we take the cube. Cube is just a solid with 6 square faces, one edge which is equal. And let's let that edge or side of the cube be A. Then the CSA or the LSA, in this case will be LSA, that is lateral surface area, because it's not a curved solid. It will be 4A square, because we are only considering the 4 faces which cover one round of that cube, right? We only consider the 4 faces, not the 2 bases, up and down bases. No, we only consider the 4 walls. Like if you have a cubicle room, then we only consider the 4 walls. That's your lateral surface area. We don't consider the top roof and the bottom floor. But if we consider the TSA, then the top and bottom are also considered, so it becomes 6A square, because each face is A square. And volume, it's a 3-dimensional figure, so A into A, that is A cube, right? Next is cuboid. Cuboid is like a rectangle kind of solid, right? So that is, it has some 4 rectangular faces. Sorry, not 4 rectangular faces, 6 rectangular faces. And it has 3 dimensions: the length, the breadth, and the height, right? Now, if you take the LSA of the cuboid, now if you take a cuboidal room, in that you have your 4 walls around you. Now, you basically have you have 4 walls, and the area of each wall is L into B, that is the length into breadth. But here, it's not a rectangle. There are different dimensions. So one will be BH, two will be LH. So 2 will be length into breadth and 2 will be B into H. That is breadth into height. Length into height and breadth into height. So two areas and two each of length into height and breadth into height. So in this you will get 2H into L plus B. And TSA you're going to consider the two top and bottom as well. So that's LB, 2LB. So you're going to consider like that, 2LB plus BH plus H. Right? And then the volume is LBH. Right? Pretty simple. Cylinder. It has 2 dimensions, the radius of the base and the height, perpendicular height between the 2 centers of the bases. Here we consider CSA since it's a curved solid. So the CSA will be that curved region, which is like if you take a pillar and the curved region of that pillar, that is your CSA. Formula is 2 pi RH. TSA, you just consider the 2 circular bases up and down. So pi r square also. So 2 pi RH plus pi r square. Take 2 pi r common, you get 2 pi r into r plus h. And then volume pi r square h. Cone. Cone is like, it has 3 dimensions. It has a slant height, which is the height of the curved surface, or the slanting height. Then we have the perpendicular height, right? We've learned this, and then the radius of the base. So there's one circular base and there's one curved area. So CSA is pi RL, right? That's the pi multiplied with radius of the base and the slant height. And for TSA, you consider the base also. So pi RL plus pi r square. So pi r common, L plus r. And volume is 1 by 3 pi r square h. This can be proved, and we basically determined with this that the volume of a cone is 1/3 of the volume of a cylinder with the same dimensions. Okay, 1/3 of the volume of a cylinder of a same dimensions. Next we come to sphere. Sphere is a round thing we see everywhere. We have so many spheres around us. The CSA of this is equal to the TSA because there's only one curved surface. There is no particular base or anything, and that's 4 pi r square. It can be determined. There's a proper proof for this, that its surface area is equal to the surface area of 4 circles, right? So we can determine it, although I'm not giving you the derivation right now. And volume is 4 by 3 pi r cube, right? Hemisphere. Hemisphere is the exact half of a sphere. The CSA and TSA in this case will be different because there's one circular base also. CSA is 2 pi r square, the half of the sphere, and TSA is the area of the base including. So 2 pi r square plus pi r square, that is 3 pi r square. And volume is half of the volume of a sphere, that is 2 by 3 pi r cube. Right? So these are the standard formulae for the solids which you will need, and you use it many times, even in class 10th, if you remember these formulas, and then just one more, that is frustum of a cone, which we will discuss in a separate video. Once you know that, well, voila, you're done. Right? So let's move forth with some concepts. Now, in this chapter, there are some concepts as well. Now, along with formula, there is some conceptual thinking which we need to understand. So let's understand those concepts for now. Now, there is the concept of recasting. Okay, recasting means that when I am melting a solid and I am converting it to another solid. So when we are converting a solid from one solid to another, then we call that recasting. Usually, we melt the main solid and then we mold it into a new solid. So that's recasting. During recasting, the shape changes, right? We can pretty much understand that the shape will change, and hence the surface area may change. Sometimes the surface area remains constant. That will be known to you. They will tell you. But in most cases, the surface area changes, right? In exceptional cases, surface area remains same. Volume will always remain constant. Regardless of this is what you need to consider, because this is the important part. Based on this, you get questions that you're converting this solid to this. Find the radius of the new solid, whatever you're being given. So you already know that the volume will remain constant. So then you can equate their volumes. You'll get one variable. You can solve that equation and get your variable. So volume will always remain constant. Right? Let's take an example to understand this. If I have a sphere of radius capital R and I'm recasting it, usually this is the symbol for recasting it into a cone of height h and radius r, small r, then the volume of the sphere will be equal to the volume of the cone because you're melting it and recasting it. So 4 by 3 pi r cube becomes 1 by 3 pi r square h. Then you can solve it accordingly. Usually you'll be given capital R and you'll be given one of these, and then you have to find the other. right? And this is just one case. You can get any other case. You can get cube to cuboid, you can get cube to sphere, you can get cube to cone. Cube to cone is usually not given. Cube to sphere, cylinder to sphere. So like this you can begin, right? So I hope that's clear. So basically the volume will remain constant. This is the consistency of volume which is the important part which you need to remember, right? Now the second concept. Now, if sometimes, what do? We have one solid A, right? And from that solid, I am removing another solid. Sometimes if it's a wooden solid, so from that I can carve out another solid, or maybe I can, maybe carve out or, shape out a new solid from a wax solid. So in this way, I sometimes take out a new solid. So from some solid A, from some solid B, we are removing a solid A. Some solid A is removed from a big solid B. So there's a big solid B. From that, I am removing some solid A. So there are two things we're going to consider here, the volume and the surface area. The volume of the remaining solid will be equal to volume of solid B, that is the big solid, minus volume of the removed solid, that is volume of solid A. Right? Pretty obvious, right? Let's take an example. For example, you have a wooden cylinder. Suppose this is a wooden cylinder. And from this wooden cylinder, I am carving out a cone of the same height. Right? Carving out a cone of the same height and the same base radius. Right? Carving out a cone of same height and same base radius. So volume of remaining solid will be volume of cylinder minus volume of the cone which has been removed. So pi r square h minus 1 by 3 pi r square h, you will get 2 by 3 pi r square h. And this will basically be the volume of this region. Volume of this region which I have just shaded. So you're getting the volume of this region by doing this, because this has already been removed, right? So all that's left is this region. So you get the volume of this region, remaining region, right? So that's with your volume, right? I hope you understood it. This is one case. You can get any other case, right? Now, if the surface area is concerned, this is a bit complex in some cases. Surface area of remaining solid will be equal to area of complete faces. Those faces which are complete. After carving, there is no effect on those faces. Plus CSA of the removed portion. So I have to include the CSA of removed portion because I removed it. Now, its impression is still left there, right? So that impression's CSA has to be considered. But other than this, in certain cases, right, as I told you, in certain cases, in some cases, you also need to add this area of removed face minus area of base of solid removed. So area of the face from which the removal has been done minus the area of the base of the solid removed. This has to be done sometimes, right? For example, we are going to take two cases. One is this case itself, this wooden cylinder. Here, what will be the surface area of the removed, surface area of the remaining solid? It will be the area, the total surface area of the solid, or not total surface area exactly. First, we're going to add the CSA. CSA will still be there, right? So CSA of solid, of cylinder, right? CSA of cylinder plus area of this base. Area of this base. So this one base is okay, right? This one base is fine. So you can include its area. Now after this, you need to include the CSA of this cone which we have removed because its impression is there, right? See? So the CSA of this cone. That's it. So the complete faces are the CSA of cylinder and base and the CSA of removed portion, which is CSA of cone, right? But in this case, we will not consider this one because when we remove the face, it is completely non-existent. No extra area is remaining, right? We have just removed the whole thing. So no extra area is remaining. Hence, we don't need to do anything with this. We just need to include these, right? But let's take another case. Suppose I have a cube, a wooden cube. And from this wooden cube, I have removed a hemispherical depression. Hemispherical depression. So, the surface area of remaining portion here will be slightly different. It will be area of 5 complete faces. That is perfectly fine. This face and then this face, then this face, then this face and this face. So, 5 complete faces will be there. So, area of 5 complete faces which have no effect by the removal. Plus the CSA of the hemisphere. So, CSA of this hemisphere needs to be considered. right? This part, it has to be considered because it's the CSF hemisphere. It has left a depression inside. So you need to include that. Plus, now here see. Can you see that this area is remaining? Even after you remove the depression, the circular base has left some of this area. So you need to include this area also. So to include that area, you take area of this one face minus area of this circle. Suppose it's some radius r. Right? So area of that circle, you'll get the area of this white shaded region. So let's solve it with the formulas. 5a square, let's assume that its edge is 5, edge is a. So 5a square plus 2 pi r square, the radius of the hemisphere is r. You will be given the radius, right? Plus 2 pi r square plus a square minus pi r square. A square minus pi r square. So you'll get this area, right? So 6a square, when you open the bracket, you get 5a square plus a square. So 6a square plus 2 pi r square minus pi r square, which is 6a square plus pi r square. And then you can substitute the values and get your total surface area of this remaining solid. Right? So I hope the concepts are absolutely clear. I've gone over the concepts of this chapter. I've gone over the formulae of this chapter. So we're pretty much done with about 75 to 80% of this chapter. And in the next video, I'll be considering frustum of a cone, in which I will tell you how to derive the formulas for the frustum of a cone also. Because there's a question in the optional exercise of the NCERT. And since the NCERT is a very old book, so they have begun asking questions from your optionals as well. Okay, so please don't consider it that it's not from examination point of view. It has started coming, and because one or two questions are always given tricky because CBSE's maths level is very high, so they keep giving you some good questions. That's why we'll consider the derivation of the frustum formulas as well, because it is a question in your optional exercises. So thank you very much for joining me. So I hope you understood everything in this video lesson. In the next video lesson, we'll be talking about the frustum of a cone and the derivation of its formulas. Thank you very much. Goodbye. Stay healthy, stay smart, and do keep studying.